All right, let's talk about impulse. So when we're talking about impulse and momentum, what we're talking about are collisions for the most part. And when we talk about collisions, a lot of people want to think car accidents, playing pool. And yeah, those are great examples of collisions, but keep in mind that a collision is any impact between two objects. Now, one thing that you got to bear in mind is that any collision involves some amount of time, right? Even if to the naked eye, it seems as if the collision happens instantaneously. So, like, say, driving a golf ball, right? The club hits the ball goes sailing off, right? To the human eye, that appears as if it happens instantaneously. But in reality, if you slow that down, right, you'll see that there's some amount of compression within the golf ball as the club hits it, and the club carries it for a while, and then the ball goes sailing, right? So every single collision that we deal with, no matter how brief, does involve some amount of time where those two objects are in contact. Um, Again, like the collision can occur in milliseconds, right? Most do. But there is that amount of time where the two objects are in contact with each other. And obviously, it's going to depend on the type of material involved, right? The collision of a foot kicking a soccer ball is going to be longer in terms of time than the collision of a golf club hitting a golf ball. Um, I'll actually make sure to link a video down here also that has a slow mo view of a golf club hitting a golf ball, so you can see that compression there. Um, so if we look at, let's say, the soccer ball being kicked, right? If we were to graph the force exerted on the soccer ball versus the time, when you have contact, well, it's going to last some time delta t, right? We're going to call that the collision time. So the foot hits the ball here. As the foot compresses the soccer ball, the amount of force exerted by the foot on the soccer ball increases up until a maximum point, and that's going to be when you've reached maximum compression. Now, as the ball starts to decompress and leave the foot, the amount of force exerted on that soccer ball decreases up until the contact ends, right? And again, notice here in the graph, it's only a matter of milliseconds. Now, you're going to see a lot of these force versus time graphs. And the reason these are important is because the area under the curve here gives us what we call the impulse, right? And so the impulse is a force acting over a certain period of time. So the impulsive force is what we call it, acting over the collision time. So if you look at your graph of force versus time, well, impulse, J, is force times change in time. Well, that represents the area underneath this force time curve. Now, obviously, the more force you apply over a greater amount of time, the greater the impulse is. Now, the best way to define impulse is an impulse will change an object's momentum, right? So if you apply that force over some amount of time, you're changing the velocity of the object. Now, typically, we're going to be measuring impulse in newtons times seconds, but we're going to use kilograms meters per second as well, and you'll see why here in a second. Also, keep in mind that your impulse is a vector quantity. It's going to be positive or negative depending on the direction of the force. So if you've got yourself a positive area underneath this curve, well, you have a positive impulse. If, let's say, we had a curve that went like this and you had a negative area, then you would know that your impulse is negative. So the direction of the impulse depends entirely on the direction of the force. Is the force positive? Is the force negative? So let's say, for instance, that we've got a rubber ball and it's bounced off the floor, and we want to know the impulse on the ball. Well, if we want to know the impulse on the ball, we've got to find the area underneath this curve, right? So what you can do is you can split this guy into two right triangles, right? And they're going to be equal in size, and find yourself the area. Now, one thing to keep in mind, and this trips up a lot of people, notice that your time in these graphs is typically going to be in milliseconds, right? Because these collisions are so fast. So when you're calculating the actual impulse or doing anything mathematical related to this graph, you want to make sure that you're converting these milliseconds into seconds. So go ahead, take a second, find the impulse acting on the ball there. All right, so what you should have gotten finding the area under the curve here is that the impulse delivered is 1.2 newtons times seconds, or 1.2 kilogram times meters per second. So that's fairly simple, right? Just finding the area. But now they're asking, what's the average force acting on the ball? Well, if we know that the impulse is 1.2 newton seconds, well, we know that impulse is your average force acting over a collision time. So this force here in this equation is the average force. Because again, if you look at the graph, notice that the force changes as the compression occurs and then the decompression occurs. So we know that we've got a impulse of 1.2 newton seconds. That's equal to your unknown force, and that collision occurs over 8 milliseconds. And again, make sure you're converting those milliseconds into seconds. So do the math, and you get an average force of 150 newtons. But again, get used to seeing these force versus time graphs because they're going to pop up a lot when we're dealing with momentum, especially in the multiple choice sections. So take a look at example 9.1. In graph A, you got the force versus time graph for a hockey stick hitting a 160-gram puck. Graph B is the force versus time graph for a golf club hitting a 46-gram golf ball. We want to know which one delivers the greatest impulse. So take a second, pause the video, work that out. Now, what you should have worked out is that the area underneath the curve, which represents the impulse, is identical for both graph A and graph B. So both forces deliver the same impulse. Yes, in graph A, you have a higher force, but it's acting over a shorter amount of time. Whereas in graph B, you've got a smaller force, but it's acting over a greater amount of time. So either way, the impulse delivered to the object is the same for graph A and graph B. Now, if we want to talk about impulse, again, earlier I said that impulse is best defined as a change in momentum. Well, let's define what momentum is first. So momentum, represented by the lowercase p in the equation, is a property of any object that is moving. So momentum is dependent upon a mass and a velocity. If something is moving and it has mass, then by definition it has momentum. The higher the mass and the higher the velocity, the higher momentum you have. So a good example of that would be a jumbo jet. The lower the mass, the lower the velocity, the smaller the momentum you have. So a good example of that would be a snail crawling through the garden. But keep in mind that anything that has mass and is moving, by definition, has momentum. So take, for instance, an electron. An electron has a very, very, very small mass. But is it moving? Yeah, right? It's zipping around the electron cloud, right? Moving all the time. So an electron, even though it has a very tiny mass, still has momentum. So anything moving has momentum. Now, the impulse momentum theorem tells us that impulse is the same as a change in momentum. So basically, if an object has an impulse delivered to it, that object's momentum changes. So for instance, if we're looking here at this hockey puck, well, the hockey puck has some amount of a momentum dependent upon its mass and its velocity here. Now, the hockey stick is going to exert a force on it over some amount of time, right? It's going to exert an impulse on it. Now, that impulse is going to change the velocity of the hockey puck, right? The mass of the hockey puck remains the same, but it's going to change the velocity of the hockey puck, thus changing the overall momentum. So that's where we get this equation FATMAV, right? A force delivered over a collision time causes a mass to change its velocity, right? So that's the impulse momentum theorem. Now, this shouldn't come as anything new to you because you've seen this equation before, right? Think about Newton's second law. Newton's second law tells us that a force equals a mass times its acceleration. Well, let's go ahead and break that down. An acceleration is a change in velocity over a change in time. Rearrange that, and you have yourself the impulse momentum equation, right? So all this is a rewriting of Newton's second law. Now, a few things with this equation. Let me write this up real big. This equation tells you a lot of things. Let's take, for instance, pitching, right? If you think about your fastball pitchers, typically your pitchers are fairly tall people, right? Well, there's a good reason for that. If you're delivering a constant force on a baseball throughout the windup, and you want to maximize that velocity at which it's going to leave your hand, right, where the baseball's mass doesn't change, the longer that you can apply that force on the baseball, the greater the velocity you're going to get. So the reason you typically have fairly tall pitchers is because, well, they have a greater wingspan. And that greater wingspan allows them to exert that force on the baseball for a greater amount of time. Another good example comes from biology, right? Look at a frog. Why do frogs have long legs? Well, again, they're able to exert a force for a great amount of time, thereby achieving a maximum change in velocity so they can jump higher, they can jump further. Now, we can also look at this in terms of stopping things. All right, picture this. You're at a water balloon throwing contest, right? Where you're tossing the balloon to one person, they toss it back to you, you guys step back, so forth. How do you catch that water balloon? Do you just catch it like a tennis ball? No, right? What do? You grab it and then you come cradle it down to the ground. Or not to the ground, but you cradle it down. Well, why do you cradle it down? Well, no matter how you catch it, this is locked in, right? You have the mass of the water balloon. The change in velocity is going to be whatever it was moving to zero, right? So no matter what method you catch it in, this side doesn't change. Now, if you can maximize the amount of time that it takes for that object to reach 0 meters per second, you can minimize the amount of force experienced by that object. So whether it's an egg being caught or a water balloon being caught, you want to cradle it down and stop it as slowly as possible so that you minimize the impact force on it, thereby, reducing the likelihood that it breaks. Right, and this is also the kind of idea you have with a lot of car safety measures. And I'll link a video that shows an old car crashing into a new car, so you can kind of see how each crash test dummy responds to the collision. But if you can maximize the stoppage time of the people in your car, you decrease the amount of force that they experience in that car accident. So good examples of that would be, well, airbags, right? Airbags slightly increase the amount of time your head comes to a stop, right? Rather than hitting a dashboard or windshield or, um, steering wheel, and thereby decreases the amount of force you feel. Right? Cars also have crumple zones. Same general idea. It's going to increase that amount of time it takes for your body to stop, thereby decreasing the amount of force you feel during that collision. And so again, that's the impulse momentum theorem, that an impulse delivered to an object changes its momentum. And again, it's just an extension of Newton's second law. Now, let's take a look at an example here. So a puck seen from above is moving with initial momentum when it receives an impulse J from a hockey stick, giving it the final momentum shown. So we want to know which arrow best represents the puck's initial momentum. So again, this puck is moving in an unknown direction, and again, this is a top view, and we know that the hockey stick gives it this horizontal impulse. And we know that as a result, the final momentum of the hockey puck is up and to the right. So take a couple seconds, maybe look at the pictures above to kind of help you out here, and determine what had to have been the initial momentum of that hockey puck. So pause, take a couple seconds, resume. So the only possible answer there has got to be D. Right, if you didn't get D right, go ahead, pause, see if you can't reverse engineer the answer, because sometimes that helps as well. Alright, so the reason it's got to be D is we know nothing about it initially. But we do know that there is a horizontal impulse directed to the right. So we know that there is a change in momentum that occurs in the rightward direction. Now, we also know that our final momentum is directed up and to the right. So again, remember, you've got to keep your components separate. So we know that there's some amount of momentum directed to the right, which could be accounted for by this, and we know that there is some amount of momentum directed upwards. Well, that momentum that's directed upwards, it had to have come from somewhere. Well, where did it come from? It means that this initial momentum had to, at least as some component, had some amount of upwards inertia or upwards momentum. Right? Because again, you can't just magically have momentum appear. So if the final has upwards final momentum, it better be present here initially, because this horizontal impulse couldn't have caused that. So the only option there when you look is D. Alright, so lastly, we've got a 10-gram rubber ball and a 10-gram clay ball. They're each thrown at a wall with equal speeds. The rubber ball bounces, the clay ball sticks. Which ball receives the greater impulse from the wall? So take a second, go through those, see if you can't reason that out, then continue the video. Alright, so the answer here would have to be the rubber ball. And the reason for that is easiest seen kind of sketching it out. So we got two balls. You got one is rubber, one is clay. They both have equal masses, they both have equal speeds, so they both have equal initial momentum. So let's just look at the clay one first. So the clay ball approaches the wall, right, with, let me sharpen my pencil. So the clay ball approaches the wall with some initial momentum we can call P, right, a product of its mass and its velocity. Now, when it hits the wall, it sticks, right? So if we're looking at the change in momentum here, and remember that impulse is a change in momentum, well, our change in momentum is your final momentum minus your initial. So your change in momentum here would be 0 minus P. So your change in momentum is just whatever this object's momentum was going to 0. Whereas your rubber ball, it's also going to have momentum P. Right? It's got the same mass as a clay. It's got the same velocity. It's going to have the same momentum. Now it hits the wall and bounces. Now let's just say, for easy math's sake, that it bounces off at the same speed with which it hits. So it's now traveling in the opposite direction with a momentum of negative P. Right? Because again, it's going the opposite direction. Momentum is a vector quantity because velocity is involved. So if we look at our change in momentum here, again, it's final minus initial. So our change in momentum would be negative P minus P. So the change in momentum would be negative 2P. Right? So the fact that it hit the wall and then bounced back in the opposite direction means that its momentum change was greater than the one that stopped. Which means, by definition, because again, the impulse momentum theorem tells us that your change in momentum is equal to the impulse, this one had to have, the rubber ball had to have received a greater impulse from the wall. So whenever you're looking at differences in impulses being delivered, right, a good place to start is by looking at the change in momentum. Now, I've posted online some basic questions there for impulse and momentum. One thing to keep in mind is depending on what they're asking for, right, you can look at this equation in several different ways, right? You can look at a force times a change in time is equal to your change in momentum. You can look at your impulse being mass times a change in velocity. Right? You can look at the fully derived equation. All right, so depending on what you're getting in your question and what you're solving for, right, all of these do the same thing. So let's say they're asking in one of the problems, find the impulse, and they've given you mass and velocity. Well, just mass and change in velocity gives you your impulse. So remember that you can derive this equation to suit your needs for the questions. So the next thing I'll be uploading will be conservation of momentum. That's the bulk of the conceptual portion for the momentum unit and the bulk of what we're going to spend our time on. So yeah, hopefully this helped. I'll post those two videos here tomorrow, along with this one, and yeah, see you in the live sessions.